Ooh, okay. Write the series for the series below. Use your series to write the second and third series. Finally determine when each series converges. So this is going to be using series we know to build series we don't know. I already did this when I talked about, like, if I have the sign of x, but then I want the sign of x squared, those sorts of series. Hopefully, this rings a bell. If it doesn't, that should look very familiar to you in the form. You have some number over 1 minus some other number. Now, when we're talking about series, that should be kicking you in the face what that is. It's the geometric series. Oh, that's right, geometric, okay. So, if we're talking geometric, the first term, so this looks like first term over 1 minus the ratio. So the first term is 1, the ratio is x, so the next term is x, then x squared, then x cubed. Oh, it's like an exponential thing that's going on there. Got it. Because we're multiplying by x each time. All right, now, notice how this is now x cubed. So instead of x, I'm going to put an x cubed. So 1 plus x cubed plus x cubed plus x cubed plus x cubed. And I guess I should write general terms here. So that's x to the n. And then the general term here is x to the, okay. So that's 0, and then 3, and then that'll be 6, and then 9. So that's going up by 3s. So 3n. And then, ooh, okay. This one looks exciting. Let's see. If I were a rich man. No, that's different. If I were to ignore the x. No, do I want to? Let's just look at this. We got a square down here, right? So I want a square down here. Well, I have an idea. If I were to take 1 minus x cubed, and I were to take the negative 1, and I were to take the derivative of that, that'd be negative 1 minus x cubed to the negative 2, chain rule, chain rule, chain rule, chain rule, chain rule, negative 3x squared. Ooh. So isn't that, get a little room here, isn't that just 3x squared over 1 minus x cubed squared? So, if I take the derivative of the left side here, I get this, which is like this. So I just rewrote it slightly to make it so things work. So if I take the derivative and multiply by a third, let's give it a shot. I'm going to put the third out front because I'm scared that I'll mess that up. But I'm going to take the derivative. So that's 0, 3x squared. That was 6x cubed, 6x to the 6th, sorry. So that's 6x to the 5th, x to the 9th, 9x to the 8th. And so that's going to be plus some stuff. I think I'll come to the general term at the end. We'll see. I could play with that now. I don't know if that'll be helpful for you. I'm going to distribute that 1/3 in. So that's going to be x squared. A third of 6 is 2x to the 5th. A third of 9 is 3x to the 8th. So the general term is whatever n is, x to the, going up by 3's each time, 2, 5, 8. So 3n plus 2, no, plus, if I plug in, I like 3n plus 2, so I'm going to leave this as n plus 1. Because if I plug in 0 for n, I get x squared and 1 in front. If I plug in 1 for n, I get x to the 5th and 2 in front. Yes, I like that. Now we want to determine when each series converges. Well, I think you can do that if you just use your understanding of geometric series. So this is when the absolute value of x is less than 1. This is when the absolute value of x cubed is less than 1, which is the same thing. This is when... Ooh, we'll have to do some more work for this one. Let's see. I think I'm going to suggest the ratio test. Let's see what happens. The limit as n goes to infinity, so that's n plus 1, so it'll be n plus 1 plus 1, which is n plus 2. X to the 3n plus 1 plus 2 over n plus 1, x to the 3n plus 2, which is going to give me I guess I'll leave that part, n plus 2 over n plus 1, because I think the second part's going to be more scary in your brains. That's going to be, let's write down what that is. That's going to be x to the 3n plus 3 plus 2, so plus 5. So subtract, so that's going to be x cubed. This goes to 1, so I still want absolute value of x cubed to be less than 1, so the same convergence, which if I were to had remembered my properties, like if I were to connect the derivative idea, domain of the derivative idea with this, since this one converges when x is less than, absolute value of x is less than 1, this one is going to converge in that same thing or smaller, because the domain of the derivative is equal to or smaller than the domain of the original function. Whew. All right. Find the Maclaurin series, then find the series for the antiderivative through the given point. All right, I will. So we have the cosine of x. I'm going to start there. Cosine of x. I know it's even, so 1 minus x squared over 2 factorial plus x to the 4th over 4 minus and so on, x to the 2n over 2n factorial. Now I want x cubed. So cosine of x cubed is going to be 1 minus x cubed squared, which is x to the 6th, plus x cubed to the 4th, which is x to the 12th, minus plus x cubed to the 2n, so x to the 6n, and then 2n factorial. And now I need to multiply by x. So that's going to be x cosine x cubed is going to be x minus x to the 6th, 7th over 2 factorial plus x to the 13th over 4 factorial plus x to the 6n plus 1 over 2n factorial plus and so on. Alright, so I did that. Then find a series for the antiderivative. Okay, so the antiderivative is going to be 1/2 x squared minus 1/8 x to the 8th over 2 factorial plus 1/14 x to the 14th over 4 factorial plus 1 over 6n plus 1 x to the 6n plus 2 over 2n factorial, and so on. Wait a minute, not 6n plus 1, 6n plus 2, silly goose. All right, but when I plug in 0, I want to get -1. Right now, when I plug in 0, I get 0, because every piece has an x in it. So if I just add a -1 there, that's like your plus c, which we've talked about before, but we've never talked about a plus c with a series before. Whew. Then this expression, which I could write equals to f of x, big F of x, that would work for my problem.